This is Team 3 with Amir, Hunter, Lena, Sam, Sankit, and Tyler, and we'll be looking into the cost optimization for a data center. The chosen system for this project is to power a 10 megawatt non-grid connected data center with the justification of the increase in demand in data centers that are planned to be connected to consumers' grids. There are 3 subsystems that will be analyzed in this system. The energy generation subsystem has an input of power demand and number of solar arrays and turbines from wind, natural gas, and coal. The energy storage subsystem will have an input of power demand and backup duration. The thermal management subsystem will have an input of power demand, waste heat, and ideal operating conditions and fluid properties. All 3 subsystems have a shared input of macroeconomic factors and a coupled output of cost. There's coupling amongst the subsystems such as the energy system downtime links the energy generation to the energy storage, and waste heat links the energy generation and storage subsystems to the thermal management subsystem. The assumption of the system is that the load of the system is a constant 10 megawatts. The energy generation will have a maximum usage of 40% renewable energy, and cost is consumed over 10 years of operation. These are the parameters defined for the 3 subsystems.
The intermediate variables shown here are divided up by their respective subsystems, with the coupling variables being highlighted. The variables for energy generation pertain to the distribution makeup of energy generation sources, the waste heat from energy production, which links to the thermal management subsystem, and the extra energy production necessary to supply the battery system. The energy storage subsystem variables focus on the amount of energy to store, and thus the sizing and cost needed to provide sufficient backup for the energy generation, and how much of that energy is currently available. The long list of thermal management variables lead through a thorough design process in order to size the heat exchanger based off the output from the generation system, and then determining the cost of building said heat exchanger. In this slide, we can see the design variables, which many of the equations on the prior slide reference, the side constraints of those design variables, and the objective function of the overall system, as well as the 3 subsystems. In the design variables, it is worth noting that the linking variables did not migrate to become a design variable, and instead stayed as the couplers mentioned previously. Design variables 5 through 8 and number 12 are real numbers, while the design variables 1 through 4 and 9 through 11 are integers designating the quantity of an item or a table index. The overall system objective function is to minimize the sum cost of the 3 subsystems. The cost for power generation comes from summing the unit cost of the energy production sources times the number of units. The energy storage cost is the sum of battery materials, energy during operation, and battery degradation. And finally, the cost for thermal management is the sum of the heat exchanger materials and pump operation.
This slide shows the full optimization model for our data center system, including all constraints and how the subsystems are linked together. On the left side, we group all of our equality and inequality constraints across all 3 subsystems. These include energy generation constraints to meet the total power demand, storage constraints to ensure sufficient backup energy and power capacity, and thermal constraints to maintain safe operating temperatures and pressure limits. Together, these constraints define the feasible design space for our optimization. On the right side, we show how the subsystems are connected at the system level. The energy generated feeds directly into the system demand, while the battery subsystem must meet both power and heat requirements. Finally, the thermal subsystem handles the total heat generated from both energy generation and battery operation. So overall, this model ensures that all 3 subsystems are not optimized independently, but instead work together as a full coupled system. This slide summarizes the key assumptions and modeling approach for our 3 subsystems. For energy generation, we assume a constant 10 megawatt load and limit renewable energy to 40%. Costs are evaluated over a 10-year period using standard generational technologies. For energy storage, we model a lithium-ion battery system where the cost depends on energy capacity, power capacity, and degradation. We also assume a fixed backup duration of 4 hours and constant discharge efficiency. For thermal management, you will use a shell and tube heat exchanger model with assumptions on operating temperatures, fluid properties, and pumping behavior to estimate heat removal and cost. Overall, each subsystem is modeled consistently using defined parameters and linkage equations, allowing us to integrate them into a single system-level optimization.
The chosen optimization method was an ATC. This was run using MATLAB. where the top level was the overall cost optimization function, and then each subsystem had its own ATC optimization within that. The ATC did remove the integer constraints from the energy generation and thermal management subsystems. This was accommodated by adding some post-optimization code to round each generation type up and then add that associated cost to the final cost. This would not impact heat generation and actually would result in a better estimate of the heat generation because this represents the capacity factor that each of the associated generation types would be running at. For thermal management, the first 3 design variables needed to be integers, and this was accommodated by rounding up those values in the lookup table for them, which consisted of the tube diameter and the tube quantity. This optimization model was run 5 times with 5 different initial conditions. These initial conditions match what was done for the subsystem optimization. The cheapest cost, highlighted in green here, came out to be just under $23 million, with the variation in cost among the 5 runs at just under $1 million. This variation in cost is mainly due to the change in energy generation portfolio. You can see some have 1 solar array, some have no wind, while others have some wind, and then each of them have 17 natural gas turbines and no coal turbines. The differences in them depend on the capacity factor that each of those generation types are run at. The heat generation the thermal management is also a contribution to the cost, with the number of tubes and the length of those tubes varying across the different iterations as well.
For our constraint sensitivity analysis, we evaluated all 10 nonlinear constraints across the generation, storage, and thermal subsystems. B2, the battery power constraint, was the only one with a non-zero coefficient at approximately negative $7,000 per megawatt, meaning that the optimizer drove battery power to its minimum feasible value, and relaxing it by 1 megawatt would reduce total system cost by that amount. All thermal systems constraints return 0, confirming that the heat exchanger has available margin on pressure drop, LMTD, and thermal duty. B3 also returns 0, not because it's truly inactive, but because a more restrictive linear state of charge window constraint is the actual binding limit. It's worth noting that linear constraints were excluded from this analysis since the perturbation method operates only on the nonlinear constraint vector. A more complete analysis would show that the state of charge window constraints carrying a non-zero coefficient as well. For parameter sensitivity, we focused on the 3 highest impact parameters identified from an initial scan of all system parameters. The normalized sensitivity metric, sensitivity times the baseline value divided by the optimal cost, allows direct comparison between parameters with different units. Cost of natural gas per unit dominates with a normalized sensitivity of approximately 0.68, which is consistent with the natural gas being our primary generation source for the 16 turbines we have. Battery energy capacity cost CE is the second largest contributor at roughly 0.29, reflecting both the high unit cost and the energy capacity required to meet our 4-hour backup requirement. Battery power capacity CP is comparatively small as well. Thermal management parameters were omitted from this chart because their contribution to the total system cost is negligible relative to the generation and storage, which together account for the vast majority of capital expenditure.
Here, we compare the optimization results at an individual subsystem and at a system level. It is evident from the columns 2 and 3 that the optimized results at subsystem level is not quite similar to the results optimized at system level, because once these subsystems are coupled, each must respond according to the requirement of the others. For generation at system level, the required mix of different generation changes. In this case, additional capacity is needed in coordination with the storage subsystem. For storage, the energy capacity changes once the storage is coupled with generation, and thermal management, as the battery needs more energy to satisfy the overall system requirement. For the thermal, more difference is seen due to the fact that heat dissipated by generation and storage is considered, which leads to changes in the overall cooling design. This highlights the criticality of coupling between different subsystems. We compared our results with real-world data center cost and found that our estimate of 22.9 million is on the lower end of the typical expected electrical system cost. From literature, we found that 25 to 35% of the total cost is attributed to electrical systems, which is roughly 23 to 65 million. The results generated from our model represents the idealized lower bound. Primary reasons are the assumptions made like constant load and not taking into consideration the infrastructure cost. The future scope includes updating the model by introducing time dependency including load fluctuation, transient events, and more sophisticated battery modeling methods. Additionally, more realistic cost components can be included to improve accuracy further. In conclusion, ATC gives us the correct framework for system level optimization, and the mentioned future work will make this framework more realistic in future.